Hi, for the first lecture of Applied Calculus, we are going to take a look at functions. We are going to explain the following concepts for today. We are going to talk about variables. We are going to talk about relationships. So let's say 1, 2 relationships. We are going to talk about functions. Then we will talk about domain and range. Next we'll talk about arithmetic operations. Then we are going to talk about composition. And next similar topic is going to be substitution. Item 8, we are going to talk about difference quotients. Item 9, we are going to talk about decomposition. Okay, that's a long list of things to talk about, but they are all short and easy to understand. Let's just go ahead and say a few words about each case. What's meant by a variable? In science, we study relationship between various quantities. These quantities typically change in time, and to reflect the fact that something that you are interested in can change, we introduce the notion of a variable. So, for example, time could be a variable, position could be a variable, price, demand, blood pressure, temperature, such things, they are all examples of variables. Well, in any kind of a scientific investigation, you want to know the relationship between variables, and these relationships can take on a variety of forms. Some of them a lot more specific than others. Sometimes you don't have a really good indication of how two things might be connected to each other, so you have some kind of a vague relationship, and sometimes you have a very precise relationship that tells you how some quantity is going to change when something else is going to change. Functions are special types of relationships. Functions are utilized in a situation where you have a set of variables. We might refer to them as input variables. And then you have another set of variables, perhaps the output variables. Typically in this course you just have one single variable as the output, but it's possible that there will be quite a few of them. When your scientific investigation tells you of a particular recipe that given a set of given numbers in the input variables, you have unique determination of the values of the output variables, you say you have a function. So a function is a rule of association that tells you how to go from input to some output. So a function consists of three portions. These input numbers together, all possible input numbers are referred to as a domain. All possible output values of the output is going to be referred to as the range. Functions, well, come with certain of recipes how to go from one set to another set. For example, if you know say the price of gasoline, can you figure out the price of a special type of plastic? What's the connection between these two? If you have a specific connection, then you have a function. So functions come with the so-called rule of correspondence that tell you the connection between the two. Let's go ahead and give an example here. So for example, we mentioned, talked about the ideal gas law. Well, ideal gas law talks about connection between following variables. If you have a container of gas, you are interested in pressure that is inside that container, the volume of that container, the temperature of that container, and the amount of gas that you actually have there. So for example, you might be looking at the tire of a car, and there's certain pressure there, there's certain volume of air inside of that tire, and the tire is held at a certain temperature. You know from everyday experience, for example, when the day is very hot, you're supposed to let some air out so that the pressure doesn't go up. Cold days, the temperature goes down, pressure also goes down, and you better pump the tire with some extra air to build up the pressure, otherwise your tires are going to wear out. So you know about the connection between these three. Well, as a scientist, you go ahead and study the situation. You figure out that in optimal circumstances, the product of pressure and volume is equal to some constant times the temperature. Let's see if we can understand this. If for a moment you consider that, for example, the volume in your tire is fixed, when temperature goes up, pressure is going to go up. Is that right? You could also imagine the following situation. Instead of a tire, you can imagine you have some kind of a piston. Perhaps here's a piston with some movable wall here, and say this is the handle of the piston here. So this wall, this purple wall, could go in or out. Suppose for a moment you insulate this chamber, this piston, so the temperature is held fixed. Now what do you think is going to happen if I press this handle inside? That is, I come, say, to this position. I just move the wall inside. Well, I'm reducing the volume, I'm compressing the air inside of a smaller volume. What do you think is going to happen to the pressure? Well, you know intuitively that the pressure is going to go up. Sometimes you want to spell that out so that you can see. You can say pressure is equal to, move the volume to the other side. This is some constant depending on what kind of a gas you have over there. Temperature divided by volume. So by now you know that if volume is a smaller number, you're dividing by a smaller number, and pressure is going to go up. We assume that temperature is constant so that we just focus on one item at a time, and so on. You can rearrange these variables in a number of ways, and various scientists have their names attached to different forms of this formula. Now if you wish, you can think of pressure as a function of these variables. Pressure is a function of temperature and volume. Now the nice thing about the function is that it gives you a unique answer. It doesn't leave anything to any kind of a debate or point of opinion or something. If you have a temperature and you have a volume, by this law we should know what the pressure is going to be. Well, what kind of relationships are there that such a thing wouldn't be so clearly spelled out? Many social situations are like that. For example, if you have a certain income, so suppose we have here's our input is income, and our output, we want to figure out what is the tax we are supposed to pay. Well, is there a function that given the income you would know what the tax is supposed to be? In a perfect world, yes, there is going to be a tax law where this is going to be very clear. But everybody has heard about loopholes and such, and different kind of interpretation of what is supposed to be income and what is not an income, and so on and so forth. So it's not all that clear what tax is supposed to be for a given income. So there is some sort of a connection between these two, but it's not all that clear what that connection is. The concept of a function is that there is no place of ambiguity left. Once the input is determined, you're supposed to have a very clear value for what the output is supposed to be. Hard sciences always strive to figure out a function that connects a bunch of input variables to a bunch of output variables. That is how you gain confidence in your prediction abilities, and that's how it increases the value of your knowledge. So functions are examples of like well-defined contracts or very well-defined laws that behave in a very rigid manner. Okay, now we are going to talk about more specifically about things that actually require a little bit of algebra. So let's leave out these science issues and the social science issues and go to some point of algebra. So what is a function notation? Function notation, well, we want to have an abbreviation for all these things that we are talking about. Our abbreviation is going to be that, okay, we said a function consists of a set of input values, a set of output values, and some form of connecting the input to the output. Well, let's choose some variable names to indicate these items for us. It would have made a lot more sense to use the letter I and the letter O and such, but tradition has it that inputs are labeled as X's, outputs are labeled as Y's, and the function or the recipe that takes you from this to that is going to be called F. So F, for example, could be the tax law, or F could be any of these kind of laws that determine situation with this ideal gas law. Function notation writes output equals to name of the function, then followed by parentheses with the input inside of that parentheses. That function notation is very compact, and later on it's going to create some problem for you. It's a kind of a inside language for mathematicians, but those who are not everyday mathematicians might find it a little bit hard to swallow, and it takes a bit of a practice to learn what is meant by this. Let's go ahead practice this. Suppose I tell you I have a function, a specific function, f of x is equal to, say, x squared plus x, a very simple function. What does that mean? Well, x is our input, y is our output, f is the name of activity, in this case this particularly given activity. Now what is going on here? Well, the meaning of this is that if I tell you the value of input is taken to be some number, say 3, then the value of the output is going to be obtained by substituting the 3 in this formula. So you take 3 and square it, and then add the 3 to it, so that's 9 plus 3, and that's 12. That is the output. Now if I take in x to be equal to, say, a minus 3, then what is the value of y? Remember, a negative number squared. Now here comes a special point from algebra 1 or 2, you might remember. This whole x being equal to minus 3, this whole thing is supposed to be squared, and then you're supposed to add that value of x to it. whenever you are dealing with a number other than the simple whole positive numbers, I recommend the students to wrap their numbers in a parentheses before they plug in it in any kind of a formula. That reduces the amount of errors you could commit. So if a number is given other than these very simple positive numbers, the best advice I could give you is from the beginning just put it in a parentheses so that things don't start getting lost and falling by the waysides and such. You will see minus right glued to the 3 right away, and you wouldn't make a mistake of moving this outside. Okay, what's on the right hand side? Minus 3 squared. We said all of these things so that you wouldn't think that this is minus 9. The other one is minus 3, and our answer becomes 6. Okay, so these activities that we went through is sometimes referred to as evaluation. You say evaluate. Okay, sometimes they might say evaluate f at 3, or evaluate f at minus 3, and so on. And then that is what you're supposed to do. Okay. Next issue in our list of issues here, see what were we going to talk about. We're going to talk about domain and range a little bit. Okay, so now we are going to talk about the domain. Okay, functions are examples of processes or machines or something like a food processor or something. It has an input and then it produces an output. Just like any other machine that has some kind of a limitation built into it, typically functions in algebra also have some limitations built into it. That is, the user should be aware of certain things that they can do and certain things they cannot do with that machine. In mathematics, typically it is the job of the user to be aware of what goes and what doesn't go. Unlike today's society where everybody is being told all the time what is it they cannot do, in mathematics it is the user's responsibility to make sure that it is using the function properly. Here are some functions that might give you some pause at the beginning. Suppose I give you, let me not give you an impression that we have to always use the letter F. Any kind of a letter would do, so long as you don't use a letter to mean two different things. So suppose I call my other function g. Okay, I define g of x to be, say, square root of x minus say 4. What are we supposed to do? Let's go ahead and practice this function. Say I tell you what is g of 8. G of 8 means you plug 8 here and figure out what it is. 8 minus 4, it is the square root of 4, and that is 2. So if you didn't encounter any kind of problem here, it just went through smoothly. What if I had said g of 7? G of 7 would have been radical 7 minus 4, that is radical 3. Well, either you sit down and patiently find it by hand, but most of you don't have that background for this. Perhaps you didn't see it in high school, figuring out the square root by hand. In these cases, most often in this course, we are going to resort to a calculator if we need to, and just go ahead and figure it out by that. So you figure out some decimal expansion for this. So you just write the exact value and some decimal value. Now, what if I had asked for g of 1? G of 1 would be 1 minus 4, and that's square root of minus 3, and that's an entirely different animal. You cannot take negative of this number and use that, because if you square it, you don't get minus 3, you again get 3. So what is the square root of minus 3? It is referred to as an imaginary number. This is an imaginary number. If people when came across this several hundred years ago, or perhaps even thousands of years ago, they didn't know what to do with it, and so the title of imaginary was attached to it. But nowadays they are just as regular of a number as anything else. However, in this course, to keep things simple, we keep to real numbers. Real numbers are just the ordinary numbers. We are giving it the adjective of real, as opposed to other things such as these imaginary numbers or complex numbers. So real numbers, just like the whole numbers, they're negatives, the fractions, radicals, some famous number like pi and so on. These are all falling inside real numbers. All sort of decimal numbers like 2.36 and so on. These are all real numbers. Complex numbers are what you make out of mixing an imaginary number with a real number. So a complex number could be like 2 as its real part, and a imaginary number attached to it. These two don't mix with each other. They're kind of like water and oil. They might sit next to each other, but their interaction is not all that trivial. Okay, now we said to keep things simple, we want to stay within real numbers. So when we are dealing with a function, we want to limit ourselves to those values that wouldn't get us to this kind of a situation. The values that will just leave us to this ordinary type of numbers, they are going to be called the domains. So domain of a function is the set of input numbers for which output is a real number. Okay, so the definition of domain is very, very simple, and so here, what would be the domain? By the way, let me recommend that in this kind of lectures, when I ask a question, you can always pause the display and think about the answer, and then resume the video and then check to see if your answer is correct or not. That way you will get a lot more out of this course. Okay, so once again, what is the domain of G? The set of all input numbers for which output is a real number. Well, if we don't want to get into the headache of a negative number inside of a radical, we have to request that this is either 0 or positive. So say to find domain of radical x minus 4, set x minus 4 to be larger than or equal to 0. Keep it away from becoming negative, and solve. Here is quite easy how to solve. You just move the 4 to either side to get x larger than or equal to 4. So that would be our answer. That is what the domain is. Sometimes they they write the answer in a fancy way, but this conveys the idea enough for this course. Sometimes they might say domain of, so they use the letter D. Domain of the function f, or what did we call it? Let me go back to see. Well, we had called it G. Let me go ahead and correct myself. This was domain of G is equal to, now we are using the letter X, so let's officially christen it to say, okay, we are going to talk about X as such that, so this vertical line stands for such that X is larger than or equal to, okay, here is equal to 4. But as I said, this is sufficient for us. Let's go ahead, take a look at another problem. Suppose I ask you, find the domain of call it now h of x. F, G, H are traditional letters used in this context. Here, say I make it, say, 25 minus x squared. A little bit more complicated than that because I have x squared in it. Well, how about working this problem on your own? What's the domain of this function? What are the x's that I can put in this, and out comes a real number. You can do a bit of trial and error if you wish, but there are systematic ways of answering it as well. You notice that if the value of x is taken to be a large number, like if you take x to be 10, let's go ahead and calculate h of 10. What is h of 10? That's going to be square root of 25 minus 10 squared. That is 25 minus 100. That is square root of minus 75. Of course, it's not a real number. So 10, that tells us 10 is not in the domain. It's not legitimate to use 10. So what is in the domain? Did you figure it out? Well, of course, x cannot exceed 5, because as soon as it exceeds 5, x squared is going to exceed 25, and you get a negative number. Okay, that is the rather easy end of the answer. X, so say x cannot exceed 5. At most, it comes up to 5. But how far down can it go? Can you figure it out? Can I put any number less than 5? Would that be fine? Can I put in this thing, for example, minus 10? Let's go ahead and see. What is h of minus 10? Well, negative or positive. When you square that input number, you get the same thing. So this is same problem as we had before, and you get a negative number inside your radical. That's again, so you could say minus 10 is not in the domain either. So we can't go down as much as what we like. What is the cutoff? Did you figure it out? The cutoff, of course, is you can't go below minus 5, because when that is squared, you are exactly at 25. Any number that's below this is going to create a bigger square, and you end up with a negative number. Okay, inside the radical. As I mentioned, it's possible to get the answer in a more systematic way as opposed to this kind of a guessing approach, but right now that might be sufficient. Later on, we are going to use the concept of inequality. You might remember that from your college algebra classes. With inequality, if you have square root of whatever and you want to figure out the domain of it, the domain is solution of, so say for square root of e, the domain is solution of e. What e stands for whatever expression you have inside of radical. So expression is an example of a mathematical sentence. Excuse me, let me take it back. It's just expression is what you can construct out of a variable and some numbers by legitimate operation. So here's your some expression inside the radical, and you want to set that larger than or equal to 0, and actually solve it. Once you solve it, the answer to that will be your domain. Let's go ahead and take another problem. Suppose I call my function say now r of x, and make it to be, say, 5x minus 1 over 2x minus 3. Question again is find domain of, no, our function is r. Well, there's no radical here, so we are not expecting to see any complex numbers or any problem of that sort. So what could be kind of a problem here? Fractions also come in with built-in headaches. That is, whenever you're dealing with a fraction, you have to make sure that you don't inadvertently divide by 0. Or if you do so, do it carefully and knowing full well as to what is it that you're doing. Okay, so whenever you have a fraction, you have to stay clear of anything that makes the denominator 0. So we just can say like this: domain of a fraction is the set of input values that do not make denominator 0. You don't want to divide by 0. So intentionally you can just go ahead and set it equal to 0, play the devil's advocate, just set 2x minus 3 equal to 0. So you solve this equation. That gives us x is equal to 3/2. Now we come on the other line, and I would say domain of R is anything other than that. This is how to write it. X is different from 3/2. Make sure you don't leave it out as this. This is not the domain. This is where we went to play the devil's advocate to figure out where is it that problem is going to occur. So domain is where the problem wouldn't occur. So you have to write it as x is different from 3/2. Another way of writing this thing is to say, or either you have to stay less than 3/2, or x is larger than 3/2. Either of these kind of numbers will be fine. So this expression, long expression, means the same thing that that one does, and the first one is easier to display, so let's just box that as our final answer. So if you are dealing with an expression that has lots of points of difficulty, it might have radicals in it, it might have fractions in it, and perhaps other things that we are going to see in the course later on, you have to get all the restrictions from each of these points of difficulties and take the intersection of all the domains, make sure at no stage anywhere in the problem you end up either with a negative under the radical sign or a 0 inside in the denominator of a fraction, or other things that we are going to see later on. So what we learn is that for square root expression you have to solve the radicand larger than or equal to 0, and if we have a fraction which has some numerator and divided by denominator, then we can say the domain of this kind of fraction is solution of denominator other than 0. So you actually have to go ahead and solve it. So please do not misunderstand me. I'm not saying that writing this out in an exam is going to be the end of it. And rather, this is the start of it. This is just what you're supposed to do in any given problem. Then you have to go ahead and solve it and say something specifically about x. So we're not asking for a definition of what is a domain, we are asking for explicit domain in any given situation, and that's what you find. Okay, what was the next item we were going to talk about? We were talking about so by now we have talked about the variables, relationships, functions, domain. Range is going to be somewhat more complicated. You understand the idea is that all the numbers that come out should be collected in one place, and that's going to constitute the range. But beyond that, I'm not going to mention anything right now until later on in the course. Let's go to arithmetic operation and compositions. So next item on the agenda is to talk about arithmetic operation. Well, from elementary school you learn about addition and subtraction and multiplication and division, and then you come to junior high, talk about exponentiation also. These things you do to numbers. Well, functions in some sense represent those numbers, so you can do exact same thing with functions. Suppose you have one function f of x, and that is say 2x plus 1, and you have another function say g of x, and that is say x squared. So two separate functions. Well, with numbers you could add them. With functions you can also add them. If I pick up the name of one function, put a plus sign, pick a name of another function, that whole thing is going to be a name of a new function. What does that new function do? That new function takes, that's the name of it. If you give it an input, what it is supposed to do is to take the output of the first one, take the output of the second one, and just add them to each other. But the language I just used is rather abstract. Essentially, you understand that if you want to add f and g, you do exactly what comes naturally. You just add the two outputs. So in this case, it would have been 2x plus 1 and x squared. So to add the name of two functions, it means that if you pick an input, the output is going to be whatever you get by adding the individual outputs. You just add them. What if you wanted to subtract two functions? Well, again, there's nothing particularly exciting about this. That means you're going to subtract the two functions. So that's going to be 2x plus 1 minus x squared. What if I want to multiply two functions? Well, I will be writing, now here's another problematic thing in mathematics. We don't use a sign for multiplication. That is rather unfortunate for outsiders. It's mathematicians' interest in making things as brief as possible, but that always creates, has a possibility of creating confusion as to what is meant. So f followed by g and nothing in between means we are multiplying two functions. And that means the output of the first one, let me write it first. So that means take the output of f, take the output of g, and multiply them. Again, you see I'm not putting anything there. In elementary school they put a multiplication sign. In computer science they put a multiplication sign. In mathematics somehow they don't, and we have to live with that. So f of x, we get the output. Now notice that if I write 2x plus 1 times x squared, that is not going to be really correct, because it's not clear what am I supposed to do here. Unless you put a parentheses, it's not going to be clear. 2x plus 1 is the output of that, x squared is the output of the other one. So you're always safe in these cases to wrap the output of each one in parentheses and then follow up with whatever you were supposed to do. If you wanted to add them, it would have been safe, also unnecessary. That is the same as what we had before. With subtraction also, this was correct, but if you put it in parentheses, you are a lot safer. Here, without the parentheses, you will have an incorrect answer. So let's go ahead. See, 2x times x squared is 2x cubed. 1 times x squared is just x squared, and we are done. Now, how about f over g? What's the meaning of putting a name of a function on the numerator, name of a function in the denominator? What does that mean? Well, that means that if an input comes, you're supposed to give it to the numerator, also give it to the denominator, and divide them. So in this particular case, let me see if I can remember who was my f and who was my g. That was my f and that's my g. So let me go back here. 2x plus 1 over x squared. Whenever you are doing division, you have to always be careful about the domain issue. What's the domain issue here? We didn't have any issues over there because none of these operations had any inherent dangers built into them. But the division does. So when you do a division, you have to keep in mind that the denominator could not be 0. So in this case, for example, x could not be 0. If I had g over f, what would g over f be? G over f is g of x over f of x. What is that? That's x squared over 2x plus 1. So what is it that I should be careful here? This whole thing wouldn't make any sense if x was minus 1/2. So I have to stay clear of that. So I don't let the denominator become 0. Okay, so we learn about these arithmetic operations. There is exponentiation as well. For example, I can think about f of x raised to the power of g. What does that mean? We don't see this thing all that much, but let me just indicate this is f of x raised to power of g of x. What was f of x? F of x was 2x plus 1. Now, without parentheses, we wouldn't be right here. Let me just 2x plus 1. And g of x was x squared. So, suppose like x was 2. What does this mean? This is 5. That is 4. And you are raising 5 to the power of 4. That is 625. Whatever that is, that's fine. Okay, that's exponentiation. What we learned here? We learned about arithmetic operations. Adding, subtracting, multiplying, dividing, exponentiating. These are exactly what you think they're supposed to be. Nothing brand new about any of them. Okay, that's what you learn in algebra. That is, very first algebra classes or arithmetic classes, you learn about addition and subtraction and multiplication and division and exponentiation. There is one thing about functions that's totally new, then that's the idea of composition. So we are going to talk about let me go and pick the same two functions that I had a moment ago. What was my f? 2x plus 1, g of x, x squared. Idea of composition is that the functions could be like machines or workers on an assembly line, that one of them is going to be the first guy who works on an incoming raw material and then produces something and passes that to the next one, and the next one works on that. So if you want to create a chain of these type of functions, we use the following notation. We use whatever worker is the first worker, we write it on the right, the next guy is going to be on the left, and we put a little circle between them, kind of a chain between these two. We are chaining these functions. Put a parenthesis around it to see, to think about it as one single unit, and here is the raw material or the input that comes in. Well, that is equal to, you have to take x, first give it to the first guy, and then figure out what that whole thing is, and then give it to the next guy. So that's the composition. So f of g is read f of g or f circle g. F of g sometimes is read as f circle, because this looks like a circle, g. Sometimes composition of f and g. Let's go ahead and practice this thing with numbers first. That would be make it more digestible, and then with symbols. Suppose I start at x is equal to, say, 3. What is g of x? So I'm taking 3, passing it to g. So that's 3 squared. That's going to be 9. Now I'm taking that and passing it to f. So everybody is going to work on output of the previous one. So f of 9 is going to be, what does f do? Takes the incoming and double it and add a 1 to it. So that's going to be 19. Go ahead and practice this thing for another input number. So I'll take 5 and see where does that go. Sometimes it might be easy to just follow with numbers. Sometimes it might be easier to actually do the algebra. So what is the answer in this case? G of x is just x squared. Now this is a point that gets a bit confusing. Can you figure out what is f of x squared? It is something that is referred to as a substitution. So what we are doing now, we are saying substitute. Okay, how does the substitution go? Let me color coordinate these things so that you see what is really happening here. Let's go to the very function f itself. Let me use a different color so that's visible. Here is the input x, and here is that input. So f of x, here the input is red, is double the input plus 1. Now we are changing our input to this. Instead of this red thing, use this green thing. That's all it means. Replace any instance of that red item with this green item. So I go on the right hand side and I write twice. Okay, here's the red one, substitute with the green one. Here's x squared, and then write everything else. In practice, of course, you're not dealing with coloring your pages with these crayons or whatever. Your best advice is to replace your x's with the parentheses around it everywhere. Take a wholesale substitution idea that you're removing that parentheses and replacing it by this parentheses. So I go ahead on the right hand side, I also put a parenthesis around it, because that's what is practical when you're actually writing your problems and such. You're not going to use colored pencils and such. So let's go ahead and practice this thing another way. Suppose I ask you find g of f of x. What does that mean? That means you take the x, you pass it to f first, and then you wrap that and you pass it to g. Okay, to make sure that we are not crowding this, let's start again here. I write my function f of x. It was, I forgot again what it was, 2x plus 1. And g of x was x squared. Let's just go practice with numbers to make sure we understand what's required here. I take x to be some number, say 5. Well, who is it going to get the 5 first? F is the one who sees it. So I say, what is f of 5? F of 5, it comes out of this formula. That's 2 times 5 plus 1, that's 11. Who goes next? G goes next. What is that G is going to see? G is going to see whatever F produced. So G is going to look at 11. And that's going to be 11 squared. It's going to be 121. So that's how it goes with a particular number in algebra. How is it going to? G of f of x. Well, f of x, here we have it, is 2x plus 1. So I go to inside parentheses and simplify that. Now I want to apply to give it to g. Well, I look at this. What does g do? G takes its input and square it. Let me go and color it one more time so that we see the one more round. After that, we are not going to be doing any coloring anymore. So here is the input of g. Here is that input. If you want to be clear, just put it in a parenthesis, even though it doesn't make any difference. Now, let me color this, the new parenthesis as well. The new input of g is this 2x plus 1. You're supposed to remove that red stuff, replace it by this green stuff. So I go ahead, instead of that I'm going to write 2x plus 1. I replace this red by the green, and then I have to square it. 2x plus 1 squared, I hope you remember from your algebra 1, that's going to be 4x squared plus 4x plus 1. If you're rusty on that, make sure you go ahead and practice a few of those things so that you're quick in those calculations. So that's a composition. We also practice idea of substitution, which is a very closely connected idea that you actually use here. One major problem that comes up in this section that's going to be very crucial for us later on is the idea of difference quotient. This idea puts together just about everything we talked about so far. Let's go ahead introduce what this thing is. Difference quotient is essentially a way that is used in all sorts of areas of science where you want to do a measurement of a perhaps sensitivity analysis, or you want to do speed analysis. So we said our functions have an input and they are taken to an output. Question that anybody faces in any area of the science: if I change my input by a certain amount, how much would the output change? Like as a physician, you might wonder, if I increase the dosage, for example, how is that going to influence the size of a tumor, or how is that going to influence the blood pressure or something. So you want to modify the input by a certain amount and figure out the influence on the output. One common way of measuring the connection here is to figure out change in the output divided by change in input. You change your dosage some amount, the say blood pressure changes by a certain amount. The ratio is a quantity that comes in handy in many areas. That's called the difference quotient. Really, the concepts such as speed, velocity, acceleration, and such, they are all examples of this concept, difference quotient. So you are going to come back to this later on. This is essentially about 60% of the course is figuring out difference quotient. That's called derivative later on, but right now we're just getting ready for the algebra of it. Suppose I am given suppose a function some function f of x, something is given. Then by difference quotient we mean f of. Now we have to use something that indicates the change in the input. The change in the input, suppose originally our input is x, later on it increases to say x plus h. It's the customary way of showing the increase. At the beginning you were x, later on it became x plus h, and then if you want to find out what's the difference, well, you subtract the two of them. How about the output? Well, you have to find the change in the output as well. The output originally corresponded to this input. It was f of x. Later on, the output came out of changing your input to something else, and the output changed also, so you write it like this. So the idea of difference quotient for the functions means, let me wrap these things in a parenthesis so that you see the connections better. X is playing the role of an input. The change in the input, well, you have to use some letter to indicate how much we changed. Here's a traditional letter used. They use H for some reason. So X is changed by H, increased by H. At the beginning, the function was f of x. At the end, became f of x plus h. Whatever this fraction is, after you clean it up, is called the difference quotient. So let's do the following. Find difference quotient for f of x is equal to, say, x squared. Well, what are the ingredients I need here? Really, the main one is just f of x plus h. Let's go ahead. F of x plus h. Now, this is an exercise in substitution. Let's remind ourselves again what's the story. This x here is going to be replaced by x plus h. So let me, maybe I said I'm not going to do this thing. I'm going back on my words. This x, here's that x. What are you doing to the x? You're squaring it. Well, instead of squaring x, square x plus h. So I'm going to write x plus h. I'm going to replace the red by this green, and do to the green whatever I was doing to the red. Important thing is that this green unit is one single unit. It has to be wrapped inside this parenthesis. Then you do things to it, not to pieces of it, but to the whole thing. So if you have x plus h squared, you remember that squaring, square the first, twice the first and second, and the second. Okay, practice your algebra so that you do these things quickly. In the numerator, here I have f of x plus h minus f of x. So let me write that down to f of x plus h minus f of x. So that's going to be all of this, x squared plus 2xh plus h squared. That is all from the first. Let me just wrap it for you so that you see this. All of it came from this first piece here. Now we have a second piece also. I have to subtract the second piece minus second piece. Let me wrap it in different colors so that you see who's goes where. F of x was x squared. That doesn't really require that much wrapping, but so this is at the beginning, this is at the end, and this is the difference. And we have now you go ahead and subtract. You get 2xh plus h squared. Well, remember, you have to have a numerator and a denominator and divide them. Well, denominator is very easy. Denominator, x plus h minus x, is always just h. So it was rather silly to write it like that. Customarily they just write an h, but I wanted to say, where did that h come from? It is last value minus the starting value. So denominator is just an h. Once you figured out the numerator, you divide by this. So we write f of x plus h minus f of x over h. This we figured it out. That is the numerator. That is the denominator. Is that the end? Not really. There is one crucial step left that is very important. It is always required that you do legitimate simplification so that the h in denominator is cancelled out. Okay, so let me state that. How do you cancel h's? Some problems is easy, some problems is really horrendous. So here is an easy example. Here we have an h. In the numerator, I can factor an h. It becomes 2x plus h. Remember, you couldn't just cancel these things out. That's not legitimate operation. You need to cancel h's, but in a legitimate fashion, not just dropping them out of the site. Now I can cancel this h, cancels that h, and out is left 2x plus h. That is our holy grail. That's what we were looking for all this time. That is the difference quotient. So let's go back, look what happened. We wanted to find the difference quotient for this function, and the answer is this. So as I said again, this concept is going to keep us busy for 60% of the course. We are going to be going around this in all sorts of different ways and explaining this thing all sorts of different ways. So make sure you practice this and understand what is involved in the algebra of it. Okay, last item I promised to talk about is decomposition. The title is not used in that fashion in the text. Decomposition means different things in different areas of mathematics. Essentially, it just means what you probably think about it right now, that if you have a function, you want to break it up to its natural components. You're decomposing it, just like a game that is made from Lego blocks, and you might break it apart, or a car that you might take it apart. Functions could also be taken apart. We talked about composition, which was putting them together. We are talking about decomposition, which is breaking them apart. We are going to talk about one type of decomposition here, and later on when we talk about integration, we'll have another item to talk about. Here, let me write a function. Write a better color. Say x squared plus 3x plus 1 raised to power of 5. Well, when we look at this function, our eyes and our mind naturally break it into two parts. And when we want to do actual evaluations or use our calculator, we really break it up into pieces. Now, how do you break it up and where do you break it up? There are many choices, and some choices look more natural than others. For example, when you want to calculate this thing on a calculator, what do you do? Suppose x is 1. You square it, triple it, and add 1. Now, let me choose x equal to 2 so that the numbers don't look like each other. 2 squared, 4, and 6 is 10, and 1 is 11. Once you are here, you're done with the parentheses. Your next job is to raise it to power of 5. So in some sense, you can say this function has a kind of a natural break here, that this is one component of it and this is another component of it. Now, if I wanted to break up this function into two pieces, what would I do? So make a function, and first of all call it something different. Let's call it h. If you want this to be a stage 1, okay, stage 1. And then the next piece, let's call it the other guy, let's call it k. That's where the difficulty comes in. Once you are done with this, what do? Whatever the input is, you raise it to power of 5. So your second activity is to take whatever the input is and raise it to the power of 5. So we are no longer thinking about all the complication here, but we are compressing all of that as our basic variable. Whatever it is, we want to raise it to power of 5. Now, what's the connection between f, h, and k? In what manner should these guys to be combined or composed to produce f? Again, pause for a moment and then come back and tell me what you got. Where do you start with? When x comes in, you first pass it to h. So far, h of x is this base. Whatever that one is, you pass it to k. Whatever k sees, he raises to power of 5. So here goes k. So f now has been decomposed to k and h, like two workers. You see h, you compose that with k, and that produces f for you. Who are h and k? These are the definitions of h and k. So decomposition comes to your mind rather naturally. Here the notation might overwhelm you as to all this abstract talking, but the idea is functions come with their natural breaks, and then you want to recognize those breaks. Okay, you go ahead and do the exercises of section 1, and I'll see you in class. Good luck and God bless.